Hello all, welcome back to our continuing series on Introduction to Atmospheric Dynamics. Today we'll be starting a new chapter, Analysis of the Dynamical Equations, where we take the equations of fluid motion that we derived in the previous chapter and begin our preliminary analysis. This analysis will allow us to better understand the connections between the qualitative behavior of atmospheric fluid flows and the quantitative behavior that we derived via the atmospheric fluid equations. The primary technique that we'll be using in order to perform our analysis will be so-called scale analysis. This scale analysis technique allows us to isolate terms from the equations of motion that are most relevant for the phenomenon that we are investigating. So shown here are the full set of atmospheric fluid equations in a vertical height coordinate. The first three equations describe momentum of the flow as basically derived as a force balance, a consequence of Newton's second law of motion. We have a continuity equation which describes the evolution of density with respect to time. It was derived from conservation of mass and relates the volume of the fluid parcel to divergence in the velocity field. We have a thermodynamic equation which describes energy of the fluid parcel and the different terms that have the capacity to modify energy of the fluid parcel. We use the ideal gas law in order to relate pressure, density, and temperature of the fluid parcel. We have a transport equation for trace gases or tracer species. For instance, moisture, which are components of the fluid within the fluid parcel, and how it moves around. And finally, we have a material derivative operator, which relates the Lagrangian frame, that is the frame following the fluid parcel, to the Eulerian frame, that is measurements at a point, and an advective term, which describes motion of the fluid parcel under a non-zero velocity field. So these equations are obviously quite complicated, and trying to understand what exactly they're describing can be initially pretty opaque. So our goal then is to simplify these equations as much as possible, similar to the technique we used in deriving the pressure vertical coordinate equations. The idea is we want to get down to a simpler form of equations which will allow us to better understand the dominant behavior of global atmospheric motion. So the preliminary motivation for scale analysis then comes from these two questions. What is the size in time and space of atmospheric phenomena that are relevant to large-scale mid-latitude dynamics? And what are the terms in the equations of motion that are most relevant for large-scale mid-latitudinal dynamics? These answers are closely connected via the usage of scale analysis. Keep in mind that for this course we will be focusing primarily on mid-latitudinal dynamics. In the mid-latitude, unlike in the tropics, we rely on a non-zero Coriolis force, which has some role in modifying the behavior of fluid parcels. And this will be important as we look at large-scale mid-latitudinal systems. Okay, so let's perform our scale analysis first on the first two momentum equations. That is, the momentum equations governing the zonal velocity u and the meridional velocity v. So these equations have a number of force terms. We see acceleration on the left-hand side, followed by two curvature terms. On the right-hand side of the equality, we have pressure gradient force, then Coriolis force, and finally viscous force on the very right-hand side. So each of the terms in this equation must have units of acceleration. This is a fundamental property of the underlying mathematics that each of the terms must have the same units associated with them as the other terms. Otherwise, this equation doesn't make any sense. So with this in mind then, acceleration is a quantity which is length over time squared. That is, it is equal to velocity divided by time, or the change in velocity with respect to time, and so it has units of length per time squared. So let's define some characteristic length unit or characteristic distance unit, capital L, and we'll define some characteristic time unit, capital T. These length and time are motivated by the particular phenomenon that we're studying. So the question is then, how do we define a time scale for a particular phenomenon. For something like a large-scale storm, one can anticipate that the length scale could be easily motivated by the diameter of the storm, but the time scale is less clear. However, we do have another notion that may be easier to understand from a particular phenomenon, and that is the velocity associated with typical fluid parcels within that phenomenon. So our idea then, in order to define a time scale associated with a phenomenon, is to say, let's take a typical trajectory and ask how far does a fluid parcel go in a characteristic time. Well, since we know that distance is equal to velocity times time, and we have a characteristic distance and a characteristic velocity, then we can define some notion of characteristic time given by t equals L over u, obtained by rearranging the characteristic equation L equals u times t. Now, this allows us to define our characteristic time then in terms of scales which are perhaps more clear for a particular phenomenon, namely length and velocity of length of the phenomenon and typical velocities within the phenomenon. So let's look at a typical tropical cyclone, for instance. The length scale is given by the diameter of the storm. The velocity scale is given by the maximum velocity associated with the flow, or a typical velocity associated with the flow. So the time scale then is the time required for a fluid parcel to move across the storm from one side to the other. So this gives us some notion then of the time unit required for communication to occur across the length of the phenomenon. And this will then give us the evolution time scale associated with that phenomenon. Okay, so we have certain scales associated with the momentum equations. We have our horizontal distance scale, we have our horizontal velocity scale, and our time scale in terms of the length and horizontal velocity scale. However, we also have a vertical structure of our phenomenon, and since the vertical structure of the atmosphere is so distinct from the horizontal structure, it's important to consider that these two scales will be significantly different from the horizontal scales. So we have a vertical distance scale denoted by h, and a vertical velocity scale denoted by capital W. Here, you'll notice that capital H seems very consistent with the notion of scale height that we defined earlier when studying hydrostatic balance. Also, from the horizontal momentum equations, we'll need some notion of typical scales associated with pressure fluctuations, because we have a pressure gradient force term that appears in these equations. So typically we define this scale to be the change in pressure over a horizontal distance divided by the density. So this then corresponds to changes in pressure which typically occur over a constant height surface. Note that this is significantly different from the changes of pressure that would occur, for instance, while going upward in the atmosphere as a consequence of vertical stratification. Okay, and the material derivative here, it represents a change on the time scale of motion. So whenever you see the ddt then, its scale is going to be given by 1 over time or u over L. Okay, so the typical phenomenon, as I mentioned, that we're going to be examining in this course are going to be mid-latitudinal storm systems, also known as extratropical cyclones. These are large-scale phenomenon that can cover a very vast distance and are responsible for instance, winter weather in the mid-latitudes, as well as basically eddy interactions and the transport of heat from the equatorial regions to the poles. These phenomena are very well studied due to their importance in understanding mid-latitudinal weather. Consequently, we know quite a bit about them. We know that typical winds within these phenomena have a velocity scale of about 10 meters per second. We know that typical vertical velocities in these systems are 0.01 meters per second, or about 1 centimeter per second. We know that the length scale is typically about 1,000 kilometers. That corresponds to 10 to the 6 meters. The height scale is given by the scale height of the atmosphere, that is the distance to the tropopause, and it has a scale of approximately 10 kilometers or 10 to the 4 meters. The time scale, denoted by L over U, can be then calculated from these quantities, and it is on the order of 10 to the 5 seconds, so approximately 1 day. Recall that 1 day is about 86,400 seconds, which has a typical time scale of 10 to the 5 seconds as well. Typical pressure fluctuations along constant height surfaces are about 10 hectopascal, or about 1,000 pascals. Typical densities are about 1 kilogram per meter cubed. And typical variations in density, that is the change in density over a constant height surface divided by the density, is about 1% or 10 to the minus 2. The Coriolis parameter has a scale associated with it. This has units of hertz or 1 over seconds. For a typical value of omega for the Earth's rotation rate of about 8.7, 1 over seconds, the Coriolis parameter, defined by 2 omega sine phi, for phi equals 45 degrees associated with the mid-latitudes, gives a scale of about 10 to the minus 4, 1 over seconds. The radius of the Earth is 6.87 times 10 to the 6 meters, or approximately 10 to the 7 meters. Gravity, 9.8 meters per second squared. Here we're going to approximate it as 10 meters per second squared. And the kinematic viscosity can be looked up in basically reference tables of typical kinematic viscosities as a function of the constituent gases. For dry air in the atmosphere, this value is about 10 to the minus 5 meters squared per second. Okay, so we now have a set of scales associated with the phenomenon that we're interested in. Let's now look at each term in the momentum equation and see what scales are responsible for determining the magnitude of that term. Well, the first term is the acceleration. This is du dt. It has scales of u over t, or substituting in t equals L over u. This term will have a scale of u squared over L. The second term is curvature associated with interactions between zonal and meridional winds. It has a scale of u squared over a, since we are dealing with the radius of the Earth, a, in the denominator rather than the length scale of the phenomenon. We have another curvature term, which looks like a horizontal velocity multiplied by a vertical velocity divided by radius. This has scales of u times w over a. We have pressure gradient force, which has scales of delta P over rho over L. Here the L is included because you'll notice that there is a horizontal derivative of pressure. The idea here being that the pressure changes by an amount delta P over a distance L. We have our first Coriolis term associated with zonal contributions to Coriolis with a value 2 omega v sine phi in the zonal momentum equation. This term has scales u times f naught. Remember, f is 2 omega sine phi, and u is the zonal velocity scale. We also have a vertical Coriolis term given by 2 omega w cos phi in the zonal momentum equation. This has scales of w times f naught. And finally, we have our viscous term, which looks like the kinematic viscosity times the horizontal velocity u divided by h squared. The reason why it's h squared is because this viscous term has both contributions from both horizontal derivatives, that is di squared di x squared, and vertical derivatives, di squared di z squared. But you'll notice that since L is much larger than h, that means that 1 over L squared is going to be much smaller than 1 over h squared, and so the dominant behavior for the viscous term will be given by 1 over h squared. Okay, so let's take these scales then and apply them to the horizontal momentum equation. We'll use the functions for scale that we derived on the previous slide and substitute in our values for large-scale mid-latitudinal systems. If you perform this substitution, you'll notice that the acceleration term has a scale of 10 to the minus 4 meters per second squared. The first curvature term has scale 10 to the minus 5 meters per second squared. The second curvature term has scales 10 to the minus 8 meters per second squared. Pressure gradient force has a scale of 10 to the minus 3 meters per second squared. The horizontal Coriolis force has scales 10 to the minus 3 meters per second squared. The vertical Coriolis force has scales 10 to the minus 6 meters per second squared, and the viscous term has scales 10 to the minus 12 meters per second squared. So this suggests that for large-scale mid-latitudinal systems, if we were to plug in what we know for the velocity field, pressure field, and density field, that the relative magnitude of these terms for large-scale mid-latitudinal systems would be given by the values listed at the bottom of this slide. You'll notice immediately that there is a dominant balance. That is, there are these two terms in these equations which are of the same magnitude as one another and are larger than all the other terms within the equation. These terms are pressure gradient force and horizontal Coriolis force. These two terms must balance each other out in these equations in order for equality to hold. That is, the perturbation from taking the difference between these two terms must be at least one order of magnitude smaller than the magnitude of each individual term. Otherwise, as mentioned before, equality could not hold in these equations. So this is interesting because this dominant balance does not include any time derivatives associated with it. That means that the mean behavior of the atmosphere must satisfy this balance between the pressure, density, and velocity field, independent of time. That is, if I was to give you a pressure field, you could then use these equations in order to estimate how the velocity field should look to a first approximation. So this is what's known as geostrophic balance in the horizontal direction. That is, it is the balance between pressure gradient forces and Coriolis forces. The reason why it is referred to as a balance is because there is no time derivative present in the system, and the system is static as a function of time. That is, we cannot use these equations in order to do prediction of future atmospheric motions, but only diagnosis. That is, we can only determine P, rho, or U in terms of two of the other variables. The remaining terms in this balance must equate in order for the equation to hold. So what does this mean? Well, you can think of it this way. Let's assume that we have a fluid parcel which is initially at rest in the presence of a pressure gradient. That is, it exists near a region of high pressure, and elsewhere there exists low pressure. So the pressure gradient force experienced by the fluid parcel will immediately initiate motion and cause the fluid parcel to start moving northwards. It will continue to experience this force as long as it's within the pressure gradient. However, once its velocity increases from being initially zero, that velocity will then trigger the Coriolis force to appear, which causes the fluid parcel to turn to the right in the northern hemisphere. Hence, as its velocity increases, the Coriolis force will become stronger and stronger, causing the fluid parcel to deflect farther and farther to the right. So it'll continue moving right until the velocity of the fluid parcel has increased to the point where the Coriolis force from that fluid parcel exactly balances the pressure gradient force it experiences. This is interesting because since Coriolis force always works to the right of the fluid parcel, and in this case we've shown that the pressure gradient force is to the left of the fluid parcel, then the path of the air parcel will actually be perpendicular to both the pressure gradient force and the Coriolis force, and the air parcel will no longer move from high pressure to low pressure, but will instead tend to move along lines of constant pressure. So, for large-scale mid-latitudinal flows, there is this intrinsic balance between pressure gradient force and Coriolis force. This balance is known as geostrophic balance and leads to air parcels traveling along lines of constant pressure. The notion of geostrophic balance is key for understanding mid-latitudinal atmospheric fluid behavior. Okay, let's look at the vertical momentum equation now. Well, we apply the same analysis technique as before. We have a dw dt, which is the vertical acceleration. This has scales of w times u over L, again obtained from w over t, where our time scale is L over u. We have a curvature term, which looks like u squared over a. We have a pressure gradient term, which looks like delta P over rho h. We have a gravity term, which looks like g. We have a Coriolis term, which looks like uf naught. And we have a viscous term, which looks like nu w over h squared. Okay, so let's look at the scales then associated with these terms. First of all, we observe that the delta P associated with the vertical momentum equations is not the typical horizontal delta P, but this is instead the delta P associated with vertical stratification. That means that we are more interested in how pressure changes over one scale height of the atmosphere. Well, since typical scale height is around 8 kilometers, and over the distance of 8 kilometers, the pressure will drop to approximately 30% of its initial value. It must be the case then that the vertical pressure scale is actually equal to the pressure at the surface, or approximately 10 to the 5 pascals. So with this in mind then, we replace the pressure scale term with pressure surface divided by rho h and continue the analysis for the remaining terms. So the acceleration term looks like WU over L. This has scales of 10 to the minus 7 meters per second squared. We have the curvature term, which has scales U squared over A. We have our pressure gradient, which has scales P surface over rho H. It has a associated value of 10 meters per second squared. Gravity also has scales 10 meters per second squared. The Coriolis term in this equation has scales 10 to the minus 3 meters per second squared, and the viscous term has scales 10 to the minus 15 meters per second squared. You'll notice again in this case we have observed a dominant balance in these equations. This time not between pressure gradient force and Coriolis, but now there is a dominant balance between pressure gradient force in the vertical and gravitational acceleration. Well, that means that if we just write these two terms out, we get 1 over rho di p di z equals minus g. But this is exactly the hydrostatic balance that we derived in the previous chapter associated with a static column of air. So that means that hydrostatic balance, describing the relationship between pressure and density in a stratified fluid, is the dominant description of the vertical structure of the atmosphere. In fact, even compared to geostrophic balance, hydrostatic balance is much, much more accurate. You'll notice that the next nearest term is the Coriolis term in this equation, and it's even 4 orders of magnitude smaller than the dominant balance shown here. Okay, so let's return to our previous question about scale analysis. What are the terms in the equations of motion that are most relevant for large-scale mid-latitudinal dynamics? Well, we analyzed the horizontal and vertical momentum equations for large-scale mid-latitudinal storm systems and found that pressure gradient and Coriolis are the most important terms for horizontal motion. This is known as geostrophic balance. And pressure gradient and gravity are the most important terms for vertical motion. This is known as hydrostatic balance. Here, note that the mid-latitudinal part of our analysis is very important because Coriolis force would not be a dominant contributor in the tropics where Coriolis force goes to 0. But in the mid-latitudes, it is a dominant driver of mid-latitudinal storm systems. Okay, so let's go back to the vertical momentum equation for a moment. Let's say that we want to use the vertical momentum equation in order to estimate the vertical velocity. Well, the vertical acceleration term, which contains the W term in this equation, is 8 orders of magnitude smaller than hydrostatic balance. That means that even infinitesimal errors made in measuring the vertical pressure structure of the atmosphere, even on the order of 1%, would lead to a completely erroneous estimate of the vertical acceleration. In fact, 0.01% error in this pressure estimate or measurement would still lead to extremely large errors in computing the vertical acceleration. Even at 0.0001% error, we're still 2 orders of magnitude larger with the errors than experienced by the vertical acceleration term. That suggests that the ability for this equation to actually estimate W is essentially non-existent. That is, this equation is terrible at estimating vertical momentum. So if we're interested then in understanding vertical momentum within the mid-latitudinal atmosphere, we're going to need to find another approach. Okay, so then that motivates the next question. How can vertical velocity be computed? Vertical velocity is incredibly important. It is a key driver for weather systems. If we didn't have vertical velocity, we wouldn't have convection in the atmosphere, and without convection, we couldn't have thunderstorms, storm clouds, or any other mechanism in order to do vertical transport of moisture from the surface to the upper regions of the atmosphere. But since W cannot be estimated from the vertical momentum equations, we cannot actually use this equation in order to understand convective storms, for instance. So the vertical velocity then must be diagnosed from some balance. That is, we'll need to find another route in order to actually estimate the vertical velocity.